Alright guys, so let's try to prove the Fundamental Theorem of Calculus Part 2. Whenever you write a mathematical proof, you want to start by kind of organizing your thoughts. So the first thing we should do is write down the assumptions of the theorem and the conclusion of the theorem, and then we'll write down anything else that we think we're going to need to use to actually prove the theorem. So the assumptions, first of all, are that f, little f, is a continuous function on an interval from a to b. Closed interval includes the endpoints. And the other assumption is that we know an antiderivative of little f, so we called that big F. So big F is an antiderivative of little f on the same interval. Okay, and before we get to the conclusion, let's write down what are called axioms. These are just facts that we know about these definitions that we've written down. So we know that an antiderivative means that if big F is an antiderivative of little f, then big F prime is equal to little f on this entire interval from a to b. Okay, why is that important? Well, that's important because if big F prime equals little f, then it means that big F, so big F is actually differentiable. Its derivative exists on this interval from a to b. Okay, so those are our assumptions, excuse me, and some axioms, which axioms are just basically unpacking the definitions that we're using. All right, and then this leads to our conclusion of the theorem. The conclusion is the big final thing that we learn from all this. And the conclusion is that the integral from a to b of f of x dx, so the integral of little f on this interval, this is just equal to the difference of capital F of b minus capital F of a. So we evaluate capital F at the endpoints of the interval, and we don't have to actually integrate over the whole interval. Well, this is saying that we do integrate, but we just do it by evaluation. Remember that this half of the fundamental theorem is called the evaluation theorem. All right, now we have to prove this. So in a mathematical proof, you have to string together a sequence of logical ideas, basically from definitions and properties of these facts that we've written down, to try to prove that this equal sign is truly an equal sign, right? So that's our whole job, is to prove that these are truly equal. And usually when there's an equal sign in an equation, proving from one direction to the other is easier. You know, there's always one direction that's easier than the other. And in this case, we have a nice definition of what it means to be a definite integral. And so let's write that down. Excuse me again. So our definition of the definite integral, we're going to work with this and try to get the equal sign on the other side. But the definite integral, we can take this as an axiom actually, because we know this definition. This is going to be the limit as capital N approaches infinity of, and I'm going to put brackets here because we're going to work on the inside of these brackets and then you pull the limit back in later. But it's the sum from 1 to n of f of xi star delta xi. Remember, this is a Riemann sum, and the key here is that we get to choose any partition that we want. So if our interval, I'm just going to sketch the interval over here without the function itself, but if our interval goes from a to b, we are allowed to chop up this interval into pieces. This is called a partition, and the rules of the partition is that x0 should always be a, x capital N, that's the number of subintervals, that should be b, and in between these x's just count up, x2, x3, etc. And so here's our rule for the partition. x0 is equal to a, is less than x1, less than x2, so these are increasing, these x values. Okay, and then finally we have b is the right endpoint of this interval. Okay, so this is what it means to be an integral, definite integral. It's a Riemann sum. And so what we're going to do next is write out, we're going to choose, so the key here is that once we've chosen a partition, so we choose this partition. And once we've chosen this partition, then the delta x is fixed. This part, once we choose the partition, delta x is just, delta xi in this case, is just the difference of xi plus 1 minus xi. All right, so we're going to need this again later. Let's remember this. We're going to need more paper here, so I'm going to turn the page. But once we've chosen this partition, we get to choose this. We know our delta xi, but what we haven't done yet is we haven't chosen these test points. So the xi star, these are in between every interval here. So let's say this is xi plus 1. Xi star can be any point in this interval. And it doesn't matter which one we choose, because when we take this limit, it's gonna be the same no matter what we choose for our partition point. So this is the key to the whole proof. So we'll go to the next page. And let's zoom in on one portion of our partition here. So let's say we have our xi and our xi plus 1. And let's even draw a portion of the curve. It doesn't have to be too crazy, but let's say this is our curve, y equals f of x, above this interval. And we know a couple things. We know that this distance between these, we've called this delta xi. It's xi plus 1 minus xi. And now what we want to do is we want to choose our test point somewhere in here, so we're not really sure where it's going to go, but the xi with a star is going to be somewhere in between this interval. And we want to choose this in a way that's going to really represent our function and take advantage of all the information that we know. So some of the information that we know is that f of x is continuous on this interval, okay? But that's it, right? The other information that we know is that we have this other function, y equals capital F of x. So this little f is continuous, but capital F of x is actually differentiable. Which, by the way, if it's differentiable, it has to be continuous. But capital F is differentiable on this interval. All right? So if it's differentiable and it's continuous, so then we learn something, or we remember something very important, and that is that we've got both continuous and differentiable, but that only applies to big F. Right? And so what we learn then is that the mean value theorem, or the MVT, the mean value theorem, this applies to capital F. All right? It applies on the entire interval from A to B, but we're only looking at the subinterval. And since it applies on all of the interval AB, it applies on this subinterval. And so what that tells us then, hopefully you remember the mean value theorem. If not, you're going to have to do a little bit of review. But the mean value theorem then says that we can find, so there is a point, or a number in this case, which we'll call c sub I, such that f prime at c sub I is equal to, so the slope of the tangent line of capital F at c sub I is equal to the difference quotient, f of xi plus 1 minus f of xi, all divided by xi plus 1 minus xi. Okay, so it says that we can find a point with this property. There might be more than one, but we can find at least one point with this property. Now, if we look at this difference on the bottom, this is just delta xi. Okay? And so rearranging this a little bit, let's not sugarcoat this. What we're going to want to do is we're going to want to choose this point that's guaranteed by the mean value theorem. We're going to want to choose this to be our xi with a star. Okay, so let's write all this out. If we choose that to be xi with a star, this down here is delta xi. The mean value theorem then tells us that for capital F, we've got this property. F prime at xi star times delta xi is equal to this difference, f of xi plus 1 minus f of xi. Right endpoint minus left endpoint. Okay? Now, one more step and then we can really get chugging with this proof. But the next step is to notice, because capital F is an antiderivative of little f, what's big F prime equal? Yeah, it's got to equal little f, right? So this whole equation now says that little f at this choice of xi star, remember we get to choose, right? So we're going to choose this xi star. So little f at xi star of delta xi, this is equal to just this difference. I'll put it in brackets. F of xi plus 1 minus f of xi. All right, so this is guaranteed by the mean value theorem. So from here, what we're going to do is plug this into our definition, our Riemann sum definition, and see what happens. All right, again, I need some more paper to actually write this out, but here's what we have. After all of our work here, so we've got, combining two ideas here. Integral f of x dx, this is equal to the limit n approaches infinity of the sum, I goes from 1 to capital N, f of xi star delta xi. Okay, before we do the sum, we notice that this, right here, we have this property, right? This magenta property right here. We can swap out the f of xi star times delta xi with just this difference that's in terms of the antiderivative. All right, so this is what gets subbed out here. So this becomes the limit. N approaches infinity. And now we still have this sum, 1 to n. But inside the sum, we now have this difference, f of xi plus 1 minus f of xi. All right, and now what we can do is we can expand out this sum. Just start counting up. And the limit's got to hang around. But what we have is limit outside, n approaches infinity, and then we plug in 1, 2, 3, etc. So when we plug in 1, I'm sorry, I guess the way that I've defined this is going plus 1 to minus 1. This should start at 0, the sum, because it's, x0 is the first number, right? So this will be then f of x1 minus f of x0. And then when we plug in 1, the next term is plus f of x2 minus f of x1. And then the next one is plus f of x3 minus f of x2. And this continues, plus, minus, etc., until we get up to f of xn minus f of xn minus 1. Okay, now something very interesting happens here. We have a plus f of x1 here and a minus f of x1 here. So those are going to cancel. We have a plus f of x2 here, a minus f of x2 here. Those are going to cancel. And this process is going to continue until we get to, say, f of xn minus 1, 3 in this case, and then minus that. So these cancel as well. And after all this cancellation, this is, by the way, this is called a telescoping sum, because it looks really long, like a long extended telescope, but then you can collapse it down. And this limit now becomes the limit, n approaches infinity, and the only things left are f of xn, which is positive. This is the positive one, and this is the negative one, right? F of xn minus f of x0. Okay, but these are constants, and so when the limit comes in, because f of xn is always, remember, in our partition, the rule that f of xn was that it always had to equal b, and xn had to always equal b, and x0 always had to equal a for any acceptable partition. And so when we plug these in, back here, we end up with the limit, n approaches infinity, of the difference between these two constants, f of b minus f of a. And as we know, the limit of a constant is a constant, right? And so this limit is just f of b minus f of a. And look at that. We've got that our definite integral equals the difference in the antiderivative. And so this is the end of the proof. And it's really just a function of the mean value theorem. When you go through this, make sure when you review the mean value theorem, review all the theorems that it takes to prove that as well. Because everything's working together to prove this theorem.